Okay, so now we're going to talk a little bit about why Caesar ciphers aren't very good. So like I said, these have been used for thousands of years, but they're actually pretty easy to break. Okay? And so what I've got up here, this is a message. It's been encoded already. I won't tell you necessarily what the shift was that it came from, but even without knowing what the shift is, you can actually figure this out pretty easily. Okay? So if you look at this message, knowing that this came from an English sentence, what's a dead giveaway here? Well, there's two things actually that you can notice here that make it pretty clear what's going on. So the first one is that one-letter word at the beginning, okay? So we've got a one-letter word at the beginning of a sentence. That is almost certainly coming from either I or A, right? There's really two one-letter words in English. And so this, if this comes from A, then that's a shift of B, C, D, E, F, G, H, I, J, K, L, M. So that's a shift of 12. Or if it comes from I, well then I, J, K, L, M, that would be a shift of 4. Okay? So right away, you've kind of narrowed this down to two possible codes. And you could easily look up, write down those two possible codes, write down a shift of 12, write down a shift of 4, and see if the rest of the message makes sense. Okay? And so this is pretty easy to break. Okay? So in general, when we think about codes, we want them to be hard to break. We want it to be hard for somebody who doesn't know how we encoded it to figure it out. You wouldn't want to encode your credit card with something this easy, right? So that's one thing that's kind of suspicious about here is this one-letter word. But there's something else that's here that also is kind of a tip-off for what this code is. And that's the letter I that appears 4 times in this message. Okay? So you may probably know not all letters appear equally often in the English language. And so chances are this I isn't standing in for something like Z or X or Q, right? It's probably a pretty common letter. In this case, it's actually coming from the most common letter in the English language, coming from E. So I, you'll notice, is a shift of 4 over from E. So E goes to F, G, H, I, so shift over by 4. And so knowing that E is the most common letter in the English language, seeing all these I's appear here, knowing that this is probably coming either from I or from A, tells you almost immediately this is a shift to 4, and you can decode the message pretty rapidly. It's I see the bear is what's actually coming from. And so you could decode that. If you want to write down a shift of 4 and practice decoding that, you can, and see that this is what you get. But so Caesar ciphers aren't very secure. And there are things that you can do to make them more secure. So to stop people from figuring out this one-letter word thing, you could get rid of the spaces, right? So if you wrote this down, rather than writing it this way, if you wrote it without any spaces, or if you broke it up into, say, like 4-letter chunks, then people couldn't say, oh, that's a 1-letter word, or that's a 2-letter word, or something like that. So that makes it a little bit harder. It still doesn't get rid of this problem of the letters being particularly common. And the other big thing that it doesn't get rid of is the fact that all of the letters are shifted by the same amount. Okay? So even if you do split things up, say you take a message, and so here's one where I've grouped all the letters together, right? So something like DROCUISCLVEO. So I've grouped these into groups of 4 letters, so getting rid of the 1-letter word or 2-letter word issue. But even something like this, you can very rapidly look through and see what are the different words that this could have come from. Okay? And you can really go through each possible code. Okay? And so there's an example of this in the PowerPoint slides if you want to see a message kind of going through. Take this first word and say, okay, if this came from a shift of 1, what did it come from? If it came from a shift of 2, what did it come from? If it came from a shift of 3, what did it come from? And what you'll see is that most of them are nonsense. So if this came from a shift of 1, so if all the letters in our original message were shifted over by 1, our original message was CQNB, right? If you shift each of these over by 1, you get DROC, right? C goes over by 1, Q goes over by 1, N goes over by 1, B goes over by 1. So a shift of 1, it would have come from this. A shift of 2, it would have come from BPMA. Also doesn't make a lot of sense. And so what you'll see, if you go through all of these, the only one that actually makes sense is if this started, if you do a shift of 10, you'll see it would have come from THES, right? And that's actually something that could be English. Unlike KKB, right? Or BPMA, THES, the something maybe, or these. A lot of different possibilities. But you can say, oh, this must be a shift of 10, okay? And so that's another real fault. There's really only 26 different codes, or 25 different codes actually, because a shift of 26 takes you back to where you started. So you only have to go through 25 different possibilities to figure out what this came from, okay? And so what you can do, you can actually replace, instead of using a Caesar cipher, you can do what are called substitution ciphers. So in a substitution cipher, rather than sending each letter to the, third one over, or the fourth one over, or the fifth one over, or whatever, I don't want to write down all of this, but you're going to randomly send these to different letters. So maybe A goes to W, and then B goes to H, and C goes to I, and D goes to Z, and E goes to A, and F goes to J, G goes to R, something like that. You assign letters to each of these. This is what's called a substitution cipher. Now, to decode a substitution cipher, you have to have the entire list of letters and where they go. Okay, so you need more information, but it also means that there's a lot more different codes. Okay, so there are 25 possibilities for where each letter goes, and so you get a lot of different possible codes. So it's much more difficult to decode. That said, it's still possible to figure it out using that frequency of letters, right? So whatever letter is most common in your message, say you find an encoded message, you're going to have a bunch of A's in it because those A's came from the bunch of E's that were in the original message. And so it can be figured out using the frequency of letters, what's called frequency analysis. So even that isn't foolproof. So what we're going to talk about in the next lecture is a different kind of cipher, what's called a transposition cipher. So I'm going to write down a substitution cipher and just go through and give you just a couple examples of how to use this. So you've actually seen one of these, and then we'll talk about transposition ciphers in our next one. So for a substitution cipher, we have to have where every letter goes. So we're going to send A, B, C, D, E to V, E, J, M, A. F, G, H, I, J is going to go to K, Z, P, SW, BXY, DF, UCR, TG, QINHOL. Okay? So notice that each letter here is represented exactly once. Some letters, like R goes to itself, that's fine in a substitution cipher, as long as not all letters go to themselves. And if you want to encode a message, so say you wanted to encode I see you, you would encode that by going to each letter and finding out what's underneath it. So S, I goes to S, S goes to T, E goes to A, Y goes to O, O goes to F, and U goes to Q. Okay? So that's encoded. If you want to decode something, like say you've got the message YVGP ST KQD. Right, so to encode, you go from the top to the bottom. To decode, you're going to go from the bottom row and figure out where it came from. So for example, you have to find Y. Y came from M. V came from A. G is over here. It came from T. P is here, came from H. S here came from I. T here came from S. K came from F. Q from U. And D from N. And so when we decode it, we get the message, math is fun, which of course is true, but it's English, which is what actually matters. So that's something that actually makes sense. So to encode, go from the top down to the bottom, to whatever the coded message is. To decode, you reverse it.